So today's topic is SQL query. Right. So for the last couple of weeks, we've been talking about how we create a schema. Right. So we've used the UML class diagrams. Right. We've to convert descriptions of requirements into an object model. Right. Into a class diagram. And so now that we have the class diagram, we then converted that into a relational database. Right. And with all tables. We talked about how to convert between the two, going from a class diagram to tables, from tables to class diagram, right? When we talk about a relational model, we talk about those tables, right, with foreign keys and primary keys that are relating to one another, right? That's a relational model, right? When we talk about class diagrams, we're more in the object model, right? We're talking about how to represent things using an object-oriented technology, right? So now that we have a database, now that we have a schema, we want to know how to interact with it, right? Meaning, all right, so I have a place to put stuff. Let's start putting data in there. And once I put it in there, how do I get it back? Okay. So we'll talk about some SQL queries. I'm sure you're already familiar with some of this. Okay. So some of this will be review for you. So yeah, so let's talk about SQL queries, SQL updates, and let's see if we can get to views today. So right, so the way we're going to interact with our relational database is through SQL queries. SQL is stands for Structured Query Language, and it has become the de facto language by which we interact with databases. And this is the typical example of a very simple select statement. And this is where what allows us to retrieve data, right? And the original intent was to make it as English as close to English as possible, so people would to lower the bar of entry to people that to use this technology, right? So you have things such as verbs such as select, insert, update, delete, right? Then you have here. From where you're retrieving data. So for instance, these are presumably the tables that we've created using the create statements. And then within those tables, you have various fields that you might want to select, right? So the data that we've inserted, presumably has been across several tables, right? So presumably we have lots of tables, right? And these tables have fields, right? So the data is going to be spread over several tables. So notice that, and each table is going to have several fields. Notice that over here it says select fields from table, right? Meaning you can tell me that I want from table 1, I want data from maybe table 1 and table 3, right? And I'll tell you which fields I want. I want that field, and that field. Right, from the two tables. So you could list here the tables and then list which fields you want of that table. Right. So now if it's one table, it makes total sense, right? I want those two fields from this table. If you have, if you have 3 records from that table, what will you get? Or what would you would expect if this is field A and this is field C? You would expect that the results from selecting that would be that you have fields A, B, and then the values for each one of them. That makes sense. But when you start asking for more than one table, that becomes somewhat weird, right? Because if you have 2 records, right? If you have 2 records in there and you have fields, this is X, Y, Z, right? So say it's field Y. What do? How do you do this? You put a field A, B, Y, and then those 2 records, where do you put them? Do they go with this one? Do they go with that one? Do they go afterwards? Are they even related? Right? Are they even related with the records of A and B? Do they have anything to do with one another? Would it make sense, right? If I have 100 records here and I have 10 records over there, how do I mix and match? Right? How are they even related to one another? Okay. So typically, what it means is that when we're asking for data from more than one table, what it really means is that we're asking for all the possible combinations, right, of all the records of one of the tables with all the records of the other table, right? So what it means is that say this is I have A1, A2, A3, and this is C1, C2, C3, right? And this is Y1 and Y2. If I'm asking that I want records from here and records from over there, then what would that mean? That means that for each one of these, for each record that I have here, I need to combine them with those records over there, right? All the possible. It's the Cartesian product of saying, take all the elements in the set T1, because it's a set, right? T1 is a set. It's a set of records, yes. And you have table T3 that also has records, right? So you have record 1, record 2, and record 3 in that set, right? And you have in T3 you have also records, right? You have let's give them names here. T1, R1, T1, R2, and T1, R3. So over here you would have 2 records, right? So you have records 1 and record 2 for table 3. Yes? So if you have a set and you ask me that you want data from both of them, what you're really asking is for the product of both, right? So all the possible combinations. So what do you have here? That means that it's T1, R1 with these 2, right? So T1, R1 with T3, R1, and T1, R1 with T3, R2. That's one of them, right? This one with these 2. And then the other one is T1, R2, again with 3, 1, R1, and T1, R2 with T3, R2. Right? So it's this one with these 2, right? And then this one with these 2 again, right? So it's T1, R3, T1, R3 twice for each one of those. Make sense? That makes sense, right? And what if you're asking for fields from these 2? Well, now you're doing that, which is a new set. That's a new set of cross multiplying these 2. Now cross multiply with T2, the records over here. Now you get a bigger set, right? You have a bigger combinatorial of each one of these. That makes sense, right? Now, at a first look, this says, okay, well, fine, but perhaps this record has absolutely nothing to do with those records over there, right? Why? Then you might ask, why even consider them? Why even consider the combination of the 2? That would make no sense, right? Typically, right? We don't consider the cross multiplication, but we consider a subset of the cross multiplication, right? Right. Only what we would do is that, yes, consider all of them, but only the ones that make sense, right? Only the ones that make sense, right? If this is a student, right? If this is a student, right? And this is a department, right? And these are all the departments, and these are all the students. Would it make sense to do the cross multiplication of all the students with all the departments? That makes no sense, right? Which ones would make sense? The only ones where that student is in that department. Yes? So we're considering a relationship between the 2. There's a relationship between one table and the other, right? Where the student knows in what department they are, right? And we can compare that department with the department ID, right? So out of all the possible combinations, we would only be interested in the cases where one field in one of these over here matches another field in the other one, right? So we would say, oh, well, this one over here, this is B, B1, B2, B3 matches, right? Y1 and Y2, right? I only want the ones where the B's matches the Y's, right? If they match, I want that. If they don't match, I don't want it, right? Okay. So now we're talking about a criteria, right? It says, yes, I want to consider all the possible combinations, but I don't want all of them as a result. I only want to filter. I want to filter the ones that make sense, where this value in one of the fields in one of the tables matches the other field in some other table. That makes sense, right? But But to calculate, notice what would have to happen, right? What would have to happen? Notice what that computing this cross multiplication. How would you do that programmatically? What would you do? For each record of that, right? You would combine it. I mean, you would have to iterate over that table, right? Because you have to consider all these records, right? And for each one of these records, you have to consider all the records on the other table, right? So for each one of these, you have to go all the way through all this table, and then you have all your combinations, and then go into the next one. And again, go all the way through. Going all the way through a table, we call that a scan. We're scanning a table, right? So we're scanning this table, and we're scanning this table, yes? As we're scanning through this, for each record, we are scanning over there. So we have a kind of like a for loop iterating over this, and for each one of these loops, we have another for loop over that. Yeah? We know that scanning through something takes order linear, right? The bigger the table, the longer it'll take us, right? But embedded in iterating over one of these, we have an embedded loop over the other one. Right, so now this is linear, but that's linear too. But you have a linear within a linear, that makes a quadratic, right? Right, so that's an order n squared, right? And if you put in there some other table, right, with T2 over here, right? That means that for each one of these, I'm going to iterate for that, and for each one of those, I'm going to iterate over this one, right? Okay. So now you're looking at cubic, right? A for loop within a for loop within a for loop. So every time you are considering several tables, T1, T2, T3, right? Student, department, section, right? You're talking about, asking the database to consider, linear, quadratic, cubic performance, right? So you have to be very, very careful when you split the data across several tables and then have to retrieve that data, right, across many tables, right? And we'll see that. We'll see later, options on how to minimize that performance, to optimize that performance, so that we don't run into quadratic or cubic performance, right? Hits, yes.
Would joining three tables be quicker than say scanning over three tables?
It depends, right? Usually, it comes out to be that the performance typically based on the indexing of the tables, right? Where you don't scan, you know where things are already, and there is no searching, right? So that you know what things you're comparing. Right? You know that you're comparing that field with that field with that field, right? It says, oh, okay, those fields would need to be indexed. So I don't scan. So I don't search them. I already know where they are, right? They are in this row. I know the 10 rows that I need to look at already. Okay, but I'm sorry, you
joining the three tables.
Yep.
Scanning speed-wise.
So scanning is always slower.
Cubic. So joining a quicker operation than.
Well, no, the scanning of one as you scan the other, that is the join, right?
Okay.
Yeah, when you say that this is equal to that, that is the join. Okay. That cross is the join. It is the join. Okay. Right. So we'll see at several techniques that can minimize this theoretical upper limit, right, on how long it'll take us. Right, we can minimize it by indexing and identifying those queries, right, those joins, right, that look at the various fields that are being joined and says, ooh, those are candidate fields, right? Those are candidate fields that I would like to index, right, to improve the performance of something like that, right? Okay, so select. Yeah, so this S here in tables, right, has a lot of implications. Right, that S over there. Anyway, so yeah, fields across several tables. And notice that at this point we don't have a where clause, right? We don't have anything. That means that consider all the possibilities, all the various combinations of all the records on one of the tables with all the combinations of the other table, right? With no filter, meaning everything. I want everything. Right, so select clause from table. Right, so the select query is going to be able to allow us to filter from several tables into a single result set, right? And out of all the tables, we're going to end up with a single temporary or virtual table, or that is going to give us the fields, which is going to be a subset of the fields from the original tables, right? And also is going to give us later when we see a where clause a subset of all the possible records that we're extracting from those tables, right? Right now there is no subset because we're not filtering, meaning we want everything, right? So the select clause basically allows us to filter, kind of like filter horizontally, right? Meaning I can choose which tables, right? Out of all the tables, I can choose which ones, and then within those tables, I can choose which fields. So we're kind of filtering horizontally. The where clause is going to allow us to filter vertically, right? To pinpoint exactly what fields, what records we want. Okay. Right, so this is the toy database that we're looking at throughout the course. If you remember, the student, the department, the course, the section, and the enrollment, right? Where notice we have 9 records for the student, 3 records for the department, 6 for the course, 5 for the section, and 6 for the enrollment. And so, for instance, here's a couple examples where we say, select, and we're saying which table from and the table, right? And then we're saying what fields we want from that particular table, right? From the student table, we say dot and then the field. In this particular case, we don't need the student prefix. Notice that our fields are being prefixed by the name of the table. We don't need it because it's only one table. It's understood, right, that it is from that table that you want these fields. But the syntax is useful when you need to disambiguate, right? If you're accessing from 2 different tables and those 2 tables happen to have fields that have exactly the same name, well, which one do you mean? You want one but not the other, or you want both, right? So you need to use the prefix to disambiguate, right? And make sure that you mean which ones do you mean? Yes.
It's necessary to use the table name. We can also just use, we can always give an alias and use that as well, right?
An alias. Yes, of course. Yes, and we'll see that in a second. So here's we didn't do relational algebra just yet. All right, I'll just skip over the relational algebra. We'll see relational algebra a little later. So like you were saying, right? We can give the tables an alias, right? And then use that alias instead of the name of the tables. Right now, again, it's not necessary. We don't need the prefix at all in this particular case. But this is going to come back and be useful later on, right? Not only because they're shorter, right? But what if you have a student table, right? You have a table that not only is it related to other tables, but you have a table that is related to itself, right? Would you have fields, right, that reference records in the same table, right? If you're trying to join them, right, you want to be able to mention that table twice, right? Because you're joining, just like you say, I'm joining T2 with T3, right? And you can mention they have unique names, right? But what if you want to be able to mention T2 twice? This allows us to do that, right? You can have T2 and then a name, right? TA, comma T2 again, and then TB, right? Both referring to the same table. Right? So those aliases allow us to do those kinds of things, to do self joins. Shorthands. Right. So right, we don't need, right, when there's no ambiguity, right, when we know exactly that there's one table, those couple fields, there's no need to even mention the alias for the table. Also, if we want over here, we get in the select clause, we can explicitly say which fields we want, right? Or you can say, well, I want all the fields. I don't want to have to tell you, which fields. I want all of them, right? And so you can just say star. You can use the star keyword, or if you have many tables, right? You can say, well, I want all the fields from this table, and then I want only these fields from this other table, right? So you can say t.star if you want all the fields from that particular table, right? And then you can list all the other fields from the table that you want, right? So here we have a very simple schema where you have a department that has ID and DNAME, And right. So right now, notice that the employee has a name and a department ID, right? Okay, and that presumably is a foreign key to the department, right? But we could have had employee instead of have name comma DID, it could have been name comma ID, right? Or even the department instead of ID, it could have been DID, right? And then when we're going to join them, when we list both tables, right? There would be two DIDs, and we would have to disambiguate them by putting the alias in front of the names. And we haven't looked at where just yet, but you see where we're going, right? Here we have a couple of examples. We have a select star from persons, returns the entire table, right? Meaning returns the table just as it is, right? With all the fields and all the records, right? Or here we can, again, we're filtering horizontally, and we want only a subset of the fields. We only want the last name and the first name, so there it is. So we don't get city, we don't get address, only first name and last name. We don't get the person ID. Now we can notice that some fields presumably are unique, like for instance PID, right? Probably that's the primary key. First name and last name, presumably they are not unique, right? Because people can have the same first name, same last name. Definitely the city is not unique, right? You can have lots of people living in the same city. If we ask for the city, right? If we retrieve the city, select city from persons, you get Lowell Dracut. But you can ask the database that I want uniqueness, right? And you say, I only want distinct. So you say select distinct city from persons. Adding distinct, notice that it adds performance, right? Because what does that mean? That means that as it's creating the result set, right? As it's creating a result, you're asking it to iterate over the result set to see if the new value is already in that result set, right? So you're asking for more work. You're asking for a for loop on the result set, right? As you're scanning, right, it's being added to the result set. If it's first going to scan the current result set to see if it's already there. If it's not there, it'll add it to the result set. If it is there, it won't add it to the result set, right? So again, all these things are you're asking for inner loops, right? Loops and loops within loops, right? There's a, as we saw when we were creating the types, right? When we're creating the create statements of the fields, there were several data types that we can use. Varchar, integers, floats, doubles, numeric, and so there are quite a few data types. Probably more data types than we need. Some of them have direct mappings to data types that we're familiar with in programming languages, right? Some data types here are very specific to the format of the vendor, right? They're vendor specific. So some of them are very standard across all databases. Some of them are very specific to that particular vendor, right? Which makes it harder to perhaps migrate from one database to the next, right? That's okay. When we get to object-oriented programming and ORMs, ORMs will handle this for us, right? We will be able to maintain the same the object model from Java or C#, and then tell it, create the schema for me, right? And it'll create the schema, the appropriate schema for whatever vendor you have, right? And the ORMs will allow us to abstract, right? Forget about the various types of representations. Also, the SQL provides an extended a library of functions, right? That allows us to manipulate the data, right? Allows us to extract things from dates. Obviously, all the arithmetic functions are there, right? There's lots of date operations. Obviously, all plus and minus. All those mathematical operations are there. You can truncate strings, or you can convert to and from string into various data types, right? For instance, you can convert strings into upper, lower. You can trim it and remove all any extraneous white spaces. You can compute the length of a string. You can do substring. So anything that you might expect that a full programming language has for manipulating strings or manipulating all sorts of data types, you can be safe that they're available in SQL. And I'm not going to go through. There's a very extensive list of functions that are available. One of them that is useful is current user, right? That's a variable it's a global variable that evaluates to the current username of the person who's logged in, right? So you can use that in queries, right? As you log in, I want to show data that is relevant to me, right? So your select statements could be generic enough, right, that include current user, so that whenever they see something, it's for that particular user who's logged in, right? You can also have / for concatenating two strings. You have like that allow you to compare patterns of strings against a pattern to see if it matches, right? So for instance, over here, you can pattern match the word Einstein, right? Pattern match it against a single character followed by I, followed by any number of characters, followed by I, followed by a single character, followed by any number of characters, right? So that would match. Does this match this? Yes, it matches. It returns true or false. Obviously, Boolean is also a data type that is supported. Here's an example of using like that allows you to pattern match various strings that match a particular pattern, right? And you have these meta characters that you would pattern match a single character or multiple number of characters, 0 or more characters. Again, every time you have a like, that's computational, right? Expensive for the database because it has to, for that particular string, it has to pattern match and see if it has to iterate, right, and see if it pattern matches that particular string, that particular pattern. So, for instance, here's an example of using that, right? You're selecting a particular column, and then you're comparing a particular column against a pattern. You're saying, I don't want all the records. I only want those records that meet this particular criteria. The where, as we'll see a little later, allow us to filter vertically, right? Vertically. So the select and the from allows us to filter horizontally, right? Which tables we want, which fields do we want in those tables, and the where clause allows us to filter vertically. Sorry. And says I don't want all the records. I only want those particular records that meet a particular criteria. Here we are comparing a particular value of a particular column against a pattern. So here we are extracting those records from the persons table for those people that has the city matches LO, right? And by default, it's lower case insensitive, right? So it will convert everything to a common case, right? And then it will do the pattern matching, right? But you can configure it to be case sensitive as well. So we're extracting all the records whose city is like LO, right? That start with LO. So Lowell, it comes back with these two records. Okay. Date data types are supported, and actually several different types of dates are supported, and different vendors support different formats. Okay. So MySQL has its family of data types, date data types. SQL Server has its own family of date data types. Here's a couple of data types. So for instance, we have usually the format is a string of the format, 4 characters for the year, dash 2 characters for the month, and 2 characters for the day. So for instance, 2008 dash 208 dash 04. And the way you declare a brand new instance of a date variable, you use the keyword date space and then the string. Okay. Intervals allow you to represent the difference between two dates, right? And the difference between two days might be days, weeks, years, right? So you can specify an interval of 5 days, an interval of 5 weeks, 5 years, 5 months, right? So there's a little in between, and then keywords here on saying how much, and there you have date operators that can compute intervals, right? How many days are there between these two dates? Right here, you have the date when this was due and the date when when it was submitted, right? And then you can query, how many days has it been between the due date and when it was submitted, right? 2 dates in a particular record, and it'll give you, the intervals that you want. So, for instance, you have here's a couple of other functions that are specific to the dates. Right? You can current date will always give you the current date, right? Extract allows you to, given a date instance, allows you to extract various parts of that date: the month, the day, the year, right? So, for instance, you can extract the month of a particular date. Now, this date over here, that's a literal date, right? It could be a field, right? It could be a field inside of as you're iterating in a select state, right? So you're extracting, for instance, a submit date, right? Might be a field in a record, right? So you can say select and then extract on that field the month, right? So you'll retrieve the month of that field. Add allows you to, given 2 dates, right? Or I'm sorry, giving a date and an interval, it allows you to add to a given date a particular interval. It'll give you a new date, right? And it's smart enough to know, the Gregorian calendar, right? Whether something is a leap year, how many days there are in a month. It will know if it's how many days a particular month it has. So, if it's December 25th and you're adding, so many days, it'll know that it has 31 days and it'll give you a date in January, right? So it's smart enough to do that. Same thing when you're subtracting, right? Again, it's smart enough to understand calendars. In particular, it's using the Gregorian calendar, right? To do date calculation. Again, as I was saying earlier, there's lots of different types of date formats, and this is vendor specific. Here's some date formats for MySQL. You have date, time, timestamp, year, right? That allow you to represent not only just a year, month, and day, but also the hour, minutes, and seconds. Some of them, different ones have different granularity, right? So some of them will go to milliseconds, right? Some of them will be going even smaller. Right? So different types have different representations. Here's some with SQL Server, date, time, small date time or timestamp, right? So this is a unique timestamp. Typically will return the seconds that occur, since 1970, January 1st, 1970, whatever. Right, and so it'll give you a UTC, world timestamp, right? That can be used across all timestamps. You can then convert that, depending on your application. You can then convert that to local time, right? Based on Greenwich time. But UTCs allow you to be independent of the particular locale. So each vendor has all sorts, a family of various functions that allow you to operate on dates, that allow you to add, subtract, get a current timestamp and current date, or format it in another format. Oftentimes, these vendors in the date format allows you to have arguments that allow you that, I want a full-blown date. So say, July 1st, 1970, all spelled out. Or if you want a much more narrow, a more abbreviated version of the date, right, where you only want, just, two digits for each one of the fields, right? 2 digits year, 2 digits month, and 2 digits day. These are some of the SQL Server. Again, they all have a slew of all sorts of functions. Here's a couple examples. If you do select, get date, select is very powerful. It's not only useful to extract data from tables, right? But it's also useful where you can give it an expression, right? It gets evaluated, and it'll return it to you as if it were a result set, right? As if it were a table, right? With a field and the various values that go with that field. So over here, when you say get date, right, it'll respond to you as if it were a new table with with a single record, with a single field, a single record whose value is 2007, 6, 6, whatever, right? Then you have, here's an example of using the convert method function that giving a value of a date and then a format. Here, I think this is using SQL. Yeah, SQL Server. This is using some of the formatting. These are constants. These are constants that are specific to SQL Server, right? That those constants mean different things. This one means that I want it in military format, right? 2007, right? Dot month, dot year. If you use just 2, it'll give you a more abbreviated version. 101 and 1 gives you an abbreviated, but a month, year, day, year, right? Representation. Oh, I'm sorry. Month, month, day, year. Right. And then 1 will give you an even more abbreviated version. Right. So the select clause I was saying earlier allows you to extract data from a particular table. But not only does it allow you to extract, it also allows you to generate data, right? Like we saw here, right? You said select, get date, right? So it was generating data from calculating the date, right? Over here, notice that it's extracting from student I think it was like 4 fields, right? I think it was student name, the ID, the graduation major, right, and something else. Yeah. Anyway, S star is extracting all the fields from the original student table. Yes. But notice that we have 2 extra fields there. One of them is being calculated on the fly, right? And it's the value is going to be the other field is graduation year. When did the student graduate? Right? So for instance, this will tell you, given the graduation year, they graduated 2007 or whatever, minus 1863, presumably the year that the college was founded, right? Will tell you how many years has it been since this student has graduated, right? So this is calculating on the fly, right? A new value, a new integer, right? A new whole number, and we are putting it under a brand new field, a brand new column that didn't exist, right? Which is grad class. So when we run this, not only are we going to have fields that come from the original table, right? Which was a student ID, student name, right? Graduation year, department ID, right? So all those are fields. Those are coming from S star, right? And the values are going to be from the original table, right? From the original table. But on the fly, we're generating 2 new fields in the result set, right? As it's iterating over the table, right? We have each one of the records. So we have all these values as we go, right? So for each one of the records, we are inserting 2 new fields. One is grad class, and the other one is the college, right? We're on the fly generating for each record, right? And the value for each one of them, for the graduating class, it'll be whatever the graduation year. So it'll subtract that minus 1863, and it'll come up with a new value. Then it's saying, under a field called college, I want always this value. Right, so I'm not calculating it, right? It's a literal. That means that this new column, it's always going to say BC, Boston College. Right? It's always going to say that. In the next record, again, it's going to take this, subtract 1863, and it's going to calculate that, and this will always be BC. So the next one is this minus 1863. It's going to calculate that, and it's going to put BC as it goes. Right? It'll come back to us as if it were a table, right? It looks like a table, doesn't it? Well, functionally, it is a table for a very brief moment, right? It generates the data. It prints it out as if it were a table, right? And but we'll see later that indeed this is a table, at least for a brief moment. Okay, the results set, we usually call it the result set, can actually be used in a larger select statement. Right? This could be an embedded select statement and then wrapped around a bigger select statement that is using this as if it were a table. Because look, it looks just like a table, doesn't it? Well, we'll see later on that we could use it as a nested select statement. Like this could be fed, the data that this is generating could be fed into another query. Okay? And we'll see that a little later. Yeah, so this comes out to be this, right? So these are all the users, the students, all the graduating class and the college, so 153. So, all these people graduated 153 years later. Wait, what? Really? Yeah, I guess so. Anyway, so here's another example on how is it that notice that we're creating. Here's another query that we're going to generate. This one is very simple, right? This one would generate what? Would generate a result set that just has the ID, the name, and the year. Just those three. This is what this query would come out to be, right? Plus, we are starting to add new things. Notice that we can rename the field name, right? So instead, I don't like SID. I don't like SID, so I'm calling it new SID, right? So we can use the keyword as, right, to rename the field name, not the value. The values is whatever the values are, right? And what else? We are renaming graduation year to graduation decade, whatever that is. What else? The name we're leaving as it is. Then we're doing what we're doing here is that we're calculating on the fly for the ID, right? For the ID, what we're calculating on the fly, the concatenation of the literal string student number and then the original student ID, right? So all these numbers are going to have, in front of them concatenated, in the result set. And in the graduation year, we're not doing anything yet. In the graduation decade, right? We're calculating the decade as we go, right, on the fly. And then the way we do this is that we take the original year, we divide it by 10, right, and we drop the decimal portion, right, and then we multiply again by 10 and bring it over just to drop the last digit. Yes, right. So first we divide it by 10. Then we cast it to an integer, right? We're casting it to an integer, and then we cast to an integer, and then the resulting value we multiply by 10 again, right? And that tells us, oh, you're the graduation from the 2000, right? 2010, 2020. What decade did you graduate, right? So it's 10, 20, 30, 40. Which decade did you graduate? That makes sense? Right. So it says here these all graduated in the decade of the 2000s. You can also have logical operators embedded in your select statements, right? As your not only can you calculate things that we're using functions, functional logic. You can also have decisions, right? Where you can compare things, right? Depending on the value of something, right? You return another value, right? So there's three syntaxes that allow you to do this. Use one of them that allow you to say, case, when, condition, then results, right? And then you can have many. This is like an if else, right? Where we're comparing. No, sorry. This one is comparing one value. This is like a switch case, right? In the switch case, you compute an expression and you compare it against many different values, right? If it's this one, then the results. Then you have a case statement, right? Which one's going to fire? This one is a little bit different because it only fires one, as opposed to in the case statement, right? If you don't have a break statement, right, it'll execute all of them, right? This one is more what we would expect. So here, for instance. Here's a very simple example where we have a very simple table with just 3 numbers, and we use a case here where we're selecting A, the original A, Right? We're selecting the original A. That means that we're going to get the original values A, 1, 2, 3, right? But we're calculating on the fly a brand new field, right? That field is generated by all the red in there. What's it doing? Let's see. Well, it's as it's iterating, right? Remember, all these selects is just what? It's a loop, right? You're looping, meaning I want to look at all the records. If it's for one table, you're looping over just one table, right? If you have in that from, if you have two tables, you're looping over this table, and for each record in this original table, you're looping over all the records in the other one, right? Correct? And you're considering all the various combinations. Over here, it's just one table. So we're looping over this, and each one, A is just 1, 2, 3. As we go, we're comparing the value of the record A, of the field A, and we say, okay, if it's A, then 1. If it's 2, then the keyword 2, meaning that in the select A, what's A? A will evaluate to whatever A is, right? 1, 2, 3. That's why the value is 1, 2, 3. Over here, the value of the second field will be either the string 1, the string 2, or the string other. Right? Where A is 1, it will be 1. Where A is 2, it will be 2. And for everything else, it will just be other. Make sense? So that red evaluates to either the string 1, the string 2, or the string other. Right? What we're missing here is the name of the field. Right? In the first one, select A. By default, the name of the field, right, is already given, right? We need to rename it. It's that field. Over here, we're not giving it a name. We're not giving the field a name. So SQL is going to guess and saying, what's the best name that I can give this field, right? And the default is to use the function, right? The original function that was used to generate that value. In this case, is the function case, right? The case keyword. So it'll by default use case, right? And this is vendor specific. Each vendor does something different, right? But ideally we would say as, right? And then give it a field name. Give it a field name that we want, and that's the field name that would appear here. Okay? All right. Here's another syntax. I'm sorry. This one is like the if else, right? The first one that matches, that's the one that I'm going to go with, right? And if else is more powerful than switch cases, right? Where if else, I can have an expression. Each if has its own predicate, right? So over here, notice that we have various predicates. Is A equal to 1? Yes. No. Is A equal to 2? So there's a predicate in each when, right? Whereas you have here a more abbreviated syntax that you have the expression only once, right? And then it's being it gets calculated only once and then compared against various options. This is like the switch case, right? It gets evaluated once and then compared against various values. So this is the equivalent, right? This is the equivalent syntax of the example we had earlier. Here's another one. Calculating the number of years since graduation. So just select star. So okay, so we're getting all the fields from the student, and then on the fly we are calculating. Let's see, what are we doing? We are taking the current dates, right? We are extracting the year. So we want to know, when did you graduate? 2014, 2013, 18. When did you graduate, right? And then we're subtracting. We're subtracting the current year is whatever today is, right? 2015, right? We're subtracting, when did you graduate? Oh, so you graduated, 2011, right? So we're calculating. You are how many years have you been an alum? Right? And that tells us we're putting under the field name, right, or column name, alum years, right? But what if you haven't graduated yet, right? Maybe you haven't graduated yet, so this would come back as negative, right? Because it's 2015 and your graduation year is 2018, so you haven't graduated yet, so it would come back as negative. 2014 minus 2018, right? So we would like to add some logic. Notice another thing that we're introducing here. We are assigning. Notice that we have Q69 equal, and then whatever the result of this is, right? So we're kind of saying that this generates a result set, right? It generates some kind of table, right? Some kind of with fields and columns and rows, right? And we're kind of storing it to be reused later, right? And there's actual syntax to do this in SQL. For right now, we're just using this abbreviated syntax, right? Where we're assuming that the results of this select, we can store it in a variable that can then be reused elsewhere, right? And we would reuse it just like you would reuse a table, because, I mean, it looks like a table, doesn't it? Right? We can use it as a table. So Q69 is holding the result set of that select statement. And here it is. We are reusing, right? We are reusing the results set generated in the previous query, right? As if it were a legitimate table, right? As if it were an actual table, right? And you can actually do that, right? You can take that select statement we had earlier, put it in parentheses, and paste it here, and that would work, right? Right. We call that embedded queries, right? We can embed a query inside of another query, right? where you can use the data generated by one query as input for another query, right? But right now, this syntax is a little more simpler, right? We're assigning it to a variable that has those results set, and then we're using it here as an input to this other query. So what is this query doing? Well, this query generated several fields in there, didn't it? Right? We generated, let's see. Obviously, we have all the fields from the original student table, yes? Plus, we have an additional field, alum years, which we generated on the fly, yes? In this one, we can so this Q69 includes all the fields from the original student plus alum years, correct? So we're using that in the outer select statement. They're saying, I don't want all the original fields from the original table, right? Meaning Q star is going to have what? It's going to have all the student table, all the student fields, right? Plus the alum years, correct? Right? And that alum years could be negative, correct? It could be negative. So here we have a case, right? We're adding another field on the fly on graduation status, right? We're saying if the alum years, as you're iterating, right? If the alum years is positive, then under the column graduation status, we're going to have a value of alum, right? Or if it's not positive, meaning it's negative, then we're going to say the value under that field will be in school. That makes sense, right? So in the case here, we would have your graduation year. We added alum years. Is that what we added, right? And this is going to be positive, negative, right? So it'll be 10 minus 2, 20 years minus 4, right? Right. So that's Q69, right? This is the student table. This is Q69, right? And then what we're adding is graduation status, right? And so this one would be our query here, right? And this is coming back as alum. Oh no, is this negative? No, alum in school, right? This is positive. Alum in school, right? That makes sense, right? Here's an abbreviated version of those case statements where you can use just a plain old if statement, right? Right. We can say, if the alum years is positive, then returns, very much like it looks like it uses the Excel syntax, right? If you check the expression, right? And if it's true, it returns the second argument. If it's false, it returns the third argument, right? It evaluates to the alum or in school. So this is true. If this is false, and that thing then goes under the graduation status column. Again, just to remind you of the tables that we're using. The from clause. So we talked about a little bit about the from clause, but we've used only one table up to this point, right? So let's talk about from clause that are considering more than one table. How are we doing with time? Okay. Right. So right now, notice that what we're saying here is student S and department D, right? Notice that we might have 40,000 students, right, across 20 departments. So just like this, you're looking at 40,000 multiplied by 20. That's how many records this would come back, right? So this would come back, a huge number of records, of results combined. That says, here this student combined 20 with 20 departments. This is the next student combined with 20 departments, and the next student 20 departments, which makes no sense, right? We would only want those combinations that make sense, right? If the student is in that department, yes, I want that, right? But notice that out of the 20 possibilities, right, I need to search, right? If I'm looking at this, if I would be filtering, which I'm not filtering, right? If I would be filtering, I have to look at the student record, right? And the filter would be, well, I got to look at the department that this student is in, right? And then match it against all the 20 departments, correct? And I have to scan the table, right? I have to iterate over the table, compare each department until I find it, right? So you have a linear search over here. Over here you have a student, also linear search. Again, you're looking at quadratic performance, right? But over here we're not filtering anything. I want the 40, 80, 800,000 records that would come back, right? If I multiply 20 and 40,000 students, yes? So it comes back with 800,000 results in the result set. Okay. In this case, we have something very simple where we have 6 fields, and this comes back with 4 fields from student and 2 fields from the department, and all the various combinations. Since we have 9 students, wait a minute, let's see. Oh, okay, no, I'm sorry. Here we're cross multiplying students with students, right? And so if there were a relationship between students, this kind of doesn't make sense, right? The better example might have been where you have maybe employees, right? You have an employee table, and you have one of the employees is a director, right? And other employees report to him. Yes? So now you have a relationship of one employee with many other employees, right? So instead of having a one-to-many where you have here is a department makes sense of one-to-many. One department has many employees, but here you have a relationship with itself where one employee is related with many other employees, right? Meaning several employees report to one employee. Make sense, right? So in this case, I would like to not only can I ask, which employees work with which department, and presumably I have a foreign key here to department, yes, right? And I can join on that. But here I want to know who reports, what employee reports to what other employee, right? So I need to pattern match a foreign key of this to a primary key of itself, right? And to do that, I would need employee twice over here, right? Employee and then employee, right? The table's twice in there, and to be able to disambiguate, which table am I talking about, right? I need to say I would need to use E1 and E2, right? And this is where it comes in handy the ability of renaming, right, or giving aliases to the tables, especially if I'm doing self joins. This is called a self join, right? Where I want to be able to join a field of one table with another field in the same table, right? So here we use the aliases to be able to disambiguate which one we want. If there are 9 students over here, this would return all 81 combinations of 9 times 9, right? The cross multiplication of all students with themselves. Here we are joining, right? We're saying, I don't want all the combinations, right? I only want the combinations that make sense, right? If I have 9 students and I have 3 departments, then the combination would be 3 times 27, right? There would be 27 possible combinations, right? But only a subset of those combinations make sense, right? Only the ones where a student is actually related to that department, that makes sense, right? So to be able to filter, we use the keyword join. I don't want all of them. I only want the ones where the student's major matches the department's ID. I only want, out of the 27 combinations, I only want a subset. All right, it'll come back how many? It'll come back with, if there's 9 students, this will come back with 9 records instead of 27. Right? Right? It'll come back with, because that's how many students there are. Now, why do we have to join in the first place? Right? That's because we normalized, right? In the first place, why is the data living in 2 different tables? Why isn't the data in the same table? Right? Because we normalized. Remember we did that, right? We ran into an issue and we said, oh, this is best if we split it into 2 tables. Yes, right? We split it into here's a student table and here's a department table, right? And we're gonna represent the department only once, as opposed to repeating the department over and over 40,000 times, right? We're gonna just represent the chemistry department only once, right? We're gonna represent the math department only once, instead of repeating the department name over and over in the students, right? We normalized, right? So whenever you normalize, when you're retrieving the data, you have to bring it back together, right? Because you're asking questions such as, when I get the student, I usually want to know in what department they're in, right? But the department information lives in another table, right? So you have to join, right? And joining, as we see, entails performance, right? We have to be careful. We have to be careful how to manage that, right? That we have to reconstruct the data, we have to join, and that entails considering performance. That's why oftentimes we go the other way around, right? Where we have a very denormalized database, right? We know the problems of normalizing. We have to join that together again, right? We have to join table 1 with table 2 with table 3, right? Now we're looking at cubic performance, right? And we usually want to, the first knee-jerk reaction is that, oh, I wish all this were in the same table so I didn't have to join so much, right? We like to denormalize, right? And that would be terrible, right? Because we went through a whole exercise of why we would normalize, right? So there's always this contention between, when you're designing, on how much you should normalize, right? Always with the making sure, looking what that normalizing would affect performance. We'll see later a technique that would allow us to have both things, right? A normalized database, right? That doesn't have any redundancy, doesn't have any risk, right? But it gives us also the ability to look at it as if it were denormalized, right? We'll see that we can use views, right? We can use views or materialized views to look at the data in a particular convenient way, right? We'll look at that a little later. Yeah, so here's a join. The syntax of joining is that you have the tables, right? And then you say, what predicate are you, how are you filtering the fields, right? Where a particular field in one of the tables matches a particular field in the other table, right? So that's a predicate. So this allows us to filter, right, vertically, right? So you say, I don't want all the records. I only want the records that match that criteria, right? So joining allows us to filter. So here we have, for instance, we have orders and persons. So let's look at we have three persons and we have 5 orders, right? Notice that the orders have a foreign key back to the primary key in persons, right? And we see that 2 orders have references to 2 existing persons, right? But one of them doesn't, right? So this one doesn't match anybody, right? So something went wrong here, right? Because this is breaking referential integrity, right? The database should have stopped us. It should have never allowed us to get into this predicament, right? If this is a foreign key to a primary key, right, the database would have never ever let us insert this because there is no primary key 15. It would have not let us insert it, right? And if there was a user with 15, it would have not let us delete it because there was a record that was referencing it, right? And that's what we call, the database enforcing referential integrity, right? Not letting us run into things like this, right? But nonetheless, we have this, because it's for academic purposes, and it'll make a point. That's what I'm trying to say, all right? But in reality, right, if these are using foreign keys and primary keys, the database would have not let us run into this, okay? And that's the whole point of using foreign keys and primary keys, right? All right, so we're joining, and it says, okay, if we didn't have the join, if we did not have the join, then we would have something like, select person, last name, first name, and the order number, and we would have said from person P, comma, orders O with no join, right? We would have come back with, 3 times 5, 15 records. That's what it would have come back to be, right? It would have been, first person and then the 5 orders, mixed in. So we would have, Dan Boone repeated 5 times, right? And for each one of those, we would have order 1, 2, 3, 4, and 5, right? And then for Bob Dole, again, repeated 5 times, right, for each one of the orders 1, 2, 3, 4, and 5. And again, Charlie Garcia, again, repeated 5 times for each one of the orders 1, 2, 3, 4, and 5. So we would have 15 in the result set with no join, right? And obviously, Dan Boone only makes sense with the order 1 and 2. Right? So that one we want. Out of those 5, 2 of them make sense. But the other 3 are bogus, right? Makes no sense. Why are you even giving me this? Right? This person has absolutely nothing to do with those 3 orders. Right? It has something to do with the first 2 orders, right? So we want to filter. We want only the ones that make sense. Which ones make sense? The ones where the person's ID matches the order's person ID, right? Now we have 3 users, right? Of which 4 orders match 2 of those users, right? And we have 1 user that matches no orders. Okay, that's okay, right? A parent is okay to have no children, right? Notice that there's a parent-child relationship here, right? The parent is the person's table, and the children are the orders, right? There's a one-to-many relationship between the parent, right, the persons, and the orders, one-to-many. One person has many orders. Yes? It is okay for a parent not to have children, right? For instance, Bob Dole has no orders. It is okay. A parent has no children. But it makes no sense for children not to have parents, right? That's what we have here, right? You have a child, it's an orphan. It's an orphan record, right? And referential integrity stops us from doing things like that, right? Right, so here we have, these are the only 4 in the results that make sense, right? There's Dan Boone with 2 orders and Charlie Garcia with 2 orders. Here, there are several types, there are several versions of the join. Okay, there's what we'll see. There's the left join, the right join, and the natural join. Right. The one we're looking at, the default. If you don't specify, it's by default we mean the natural join. Right. The one that makes sense. Right. The one that you're pattern matching. Right. One field with the other field. But what about the ones that don't match? What do we do with those? Well, the intuition is to say, well, they don't match. They make no sense. Why would I even want them? Okay. And in most cases, we would be right. In most cases, yes, that is true. Right. If you have students and each student is in a department, and I want to match what students goes in what department, then it tells me, well, these are all the students and these are all the departments. But that assumes something saying that all students are in a particular department. What about students that are undecided, right? That are not in a department. So they have no declared major. What about those records? Are they ignored? Well, it depends what question are you making, right? If you're asking something that has to do with all students in the university, then they can't be ignored, right? So that's where left and right come in, right? Where yes, I want the ones that match, and if they match, I want the data from the matching table. But I also want the ones that don't match, right? Right? Because maybe I want to know the students, right? All the students. If I know what department, I want to know what department they are in. But if they have no department, I still want to know who they are, because I'm going to send some letter or some emails or whatever, right? I want to send it to all the entire student body, right? If I know their department, I'll include some blurb about the department. If I don't have the department, then I won't include the blurb about that department. Make sense? So that's where left join and right join come in, where I might want those that don't match as well. Okay, so let's look at those. So here we have left join, where you have table 1 and table 2. That means that it says, I want all the records from table 1, even the ones that don't match. Right? But if they do match with table 2, I want the records from table 2. If they don't match records from table 2, it's okay. I don't want the data from table 2. I'll just keep the data from table 1. Okay? So let's look at an example, right, where we have here, and that's why we have this orphan. That's why we have that orphan there. Notice that I have an order that doesn't match the parent, and I have a parent that doesn't match the order, right? Right. That I did that on purpose. So we have the original 2 tables, and we do a left join. Notice that we're doing person join with the orders. We have the original 4 here, right? Here are the 4 that make sense, right? The ones that do match. But I wanted all the persons, even the ones that did not match. Okay? So I definitely have Dan Boone, 2 for those 2 orders for Charlie Garcia. And here's Bob Dole, who has no orders. All right, so I would get a null. I would get a null for there is no matching for the right hand side. And left join means that the table who I want the records from, even if they don't match, is the one on my left. Right? Or I can say the one on my right. Okay, the ones on the right hand side. Right? Let's look at the right hand side. So here's an example. Why would you do this? Why would you ever do this? Right? I already gave you an example, right? Maybe you have some students. Some students don't have a match with their department, but you want the students anyway, right? So here's an example where you have staff, and the staff has a spouse, presumably a 1-to-1. So the staff, and that staff might be married or not, right? And I want to know all the staff members, right? And the query might be that yes, retrieve all the staff members. Yes. If they're married, I want to know who their spouse is, right? If they're not married, I still want to know who the staff is, right? So we have 2 tables here, right? And here's usually in your query, right? And your query might say, I want find the name of each staff member and their spouse. Well, that tells me that I need to join the staff with the spouse, obviously, right? And if it's just that, right? If that's the entire query, it's just a natural join, right? But if adding this additional 2 words here tell me that, oh, wait a minute, you want, because it says if any, right? I want the spouse, if any, meaning if there is a spouse, yes, I want it. But if they don't have a spouse, I still want the staff, right? So that tells me that I need to do a left join on each one. And I thought I had an example. I guess I don't. Oh, yes, I do. Here we go. So the inner join, or also the natural join, right? The join that we would normally do, right? Is that we would match only the ones that match only the ones that make sense, right? It would throw out the ones that don't match, right? So in this one, it says we're matching the fields in the staff social security number matching with the spouse social security number. If they match, I want them. But this is only going to return what? It's going to return only those staff members that are married, right? It's going to ignore all the staff members that are not married, right? That don't have a spouse. So that doesn't work. So it has to be either a left join or a right join, again, depending on where I have the staff and where I have the spouse. So it says I want the staff, even if they don't match, I want them as well. And all the fields from the spouse, just make them null, right? If they don't match. Right join is just the same thing, right? It's only relative, right? Relative to where they are, the position of the table, whether it's to my right or to my left. Oftentimes, these are these predicates are it's you have several predicates, right? Join with this, join with that, join, right? And it's the results from the previous join, feeds into the join of the second join, right? So it says, it's the left, whatever I have plus this, I'm joining this with whatever on my left, right? So I'm writing from left to right, right? And I'm adding more and more joins and more criteria that I want to join. Let's look at an example where we would have different types of join. Okay, so we're going to do another example, sorry. We're going to right join, right? Before, we also had persons on the left and orders on the right-hand side. But now we notice that we have the right join. On the left join, it was returning the data from the persons, right? That didn't match. Over here, with the right join, is returning the data from the orders that did not match. Okay, right? So it's here's the orphan, right? The orphan order that didn't have anyone that's coming back, and it has no matching with the person table. Full join is just I want everything, right? It says I want, definitely I want the ones that match, right? From the first table. Definitely I want the ones that match from the right table, right? And then everybody else that doesn't match, I want them too, right? So first tell me all the ones that match first, then tell me all the records that don't match from one of the tables, and then the ones that don't match from the other table. Okay, and so here's an example, from these two tables. If we do a full join, here are the ones that did not match with the order table, and here's the ones that don't match with the person table. Right, you get nulls on each side. Okay. As I was saying earlier, you can nest joins, right? Where first you join two tables. Joins only works on two tables at a time, right? So I first join these two tables, right? And then the results of joining that table, or whatever records come back from that, right? Now I'm going to cross join with another table, right? So whatever that came back, now I'm going to filter again, right? And then I filter again, and then I filter again, right? Because again, it could be that we have our data across several tables, right? So I need to fetch some data from this table, some data from that table, and data from that table. And the way they communicate is this one has a foreign key to that one, and this one has a foreign key to that one, right? So first I have to join these two. So whatever records I have, right? So that's a filter on these two on the predicate on these two tables, and then whatever has this foreign key to that, right? I need to join on this one, right? So the syntax is you can use parentheses, right? Which says I'm joining first a student with enrollment, right? On the foreign key SID to the I'm sorry, it was. SID is the student ID, that's a primary key, and the foreign key is in the enrollment student ID. That's a foreign key, right? So we're matching those two. Once I calculate that, whatever that comes back with, I am joining that with the section ID, right? So once I join that, I still have the enrollment student enrollment record that has a foreign key to the section table, right? Has a foreign key to the section. So this one, we're first joining, if you remember, was something like this, right? you have the student, and you have the enrollment, and you have the section, right? And this one has a foreign key here and a foreign key there, right? So this one had the K and the student foreign key. So this was one-to-many and one-to-many like that, right? Right? Is that what we had? Something like that? So foreign key, foreign key. So first we're joining these two, right? We're joining that foreign key against this primary key. The result of this, which might be a subset, right? A subset of records. Those records I'm filtering even more, right? I don't want all of them. I only want the one that match that particular student was in that particular section, right? So I don't want to know all the students in all the that are enrolled. I only want to know for this particular section. Right? So if I give you the section, then I can tell you, right, by section. So notice that this could get very hard to read, right? This join with that join. So it could keep going, right? So it can get very, very hard to read. For that, we have an alternative syntax. There is an alternative syntax that many find a little easier to read, right? A little easier to read. Instead of having all the predicates on the join, right? Instead of having the predicates on the join, we can have exactly the same predicates on the where, right? Right? All those predicates, you can just say from in the two tables, right? The two tables, right? So the same two tables that you were joining first, right? The same two tables, right? But the predicates, you put them in the where. Now this is much easier to read, right? This is much easier to read, right? Although, nonetheless, the above one is still preferred, right? The above one is easier for databases to make certain types of optimizations, right? Where it knows that you're joining these couple of fields, right? So it knows that it can pre-calculate certain things, right, to optimize that query. Whereas over here, the joins is implied, right? This one is very explicit. We're saying what fields we're joining, right? Over here, we're not we're just saying we're iterating, and when they are equal, I want it, right? That's kind of what we're saying over here, right? Meaning, loop through the whole table of one of them, loop through the whole table of the other one, right? Whenever you see that these match, I want that record, right? That's basically what we're saying over here, right? So it's an implied join, right? It does the same thing. It does exactly the same thing. You get the same exact result. But that one is we call it an explicit syntax, right? Where we know that this is going to be a join, right? I know I'm going to have to iterate over this. I can check to see if there's certain indexes, right, that have been already pre-calculated, right? Instead of iterating, right, I can say, oh, there's indices. I'll use the indices instead, right? I can plan. The database makes plans on how to optimize these things, right? This gets us into the where clause. Let's break for a little bit, and we'll do the where clause when we come back.
你在那边忙杀死我，你是猫尿。
呀，我操！我有点挂了，
超丑，我觉得看不起。
我也感觉这样子。这个看运气。这个就我
要明天我去。
关于没有加急吧？加急的话就1000，加急了100块钱嘛。
明天我
11场上，哎，花了多少钱？没给我呀。乘以2，花了280。国内选项嘛，没说。对，在国内口碑非常。你真的吗？
完全。
Yes. My group currently has 2 good ideas for the project.
Okay.
The first question is, when was the abstract due? I thought it was due today.
Yes. Well, this weekend. Yes.
At any point? Like, do we just,
Yeah, this weekend. Right.
do we just email it to you?
No, I'll make up a submission where you can submit it.
Okay.
Okay. And you can either submit as a PDF or ideally it's in Word in Google Docs, and you can get a link to sign it or something like that.
Is there any specific length that you're looking for about it?
Just a couple paragraphs.
Okay.
Yep.
And secondly, the group, we currently have 2 good ideas for the project. What's the best way of deciding? Like, do we just flip a coin, or can we email to you? And
you can provide both of them described in on the same document. Idea 1, idea 2.
Okay.
And I can give you feedback on which one.
Which one sounds more feasible?
Yeah.
Long one. Okay, that sounds good.
Yeah.
Thank you very much.
All right. What's up?
This is regarding an idea for the project. Just wanted to put
Yep.
through the idea and then
Okay.
wanted you to decide whether it's too simple to not work on it or not.
Yeah.
So one
All right, let's continue. All right, so the where clause. All right, so we've talked already a little bit about the where clause here and there. And basically, I used the fact that you can join as a okay. Oh, right. So I used the fact that you can use those predicates that we were using in the join clause, right? We moved them over to the where clause. Right? So that was my segue into the introduction of the where clause formally. We have looked at where clause already informally, and basically what we do in the where clause is that we provide predicates, right? So the top half, right, the select and the from says, just consider all the possible combinations of fields and records from all these tables. Yes, right? Whereas the where clause tells us, wait a minute, I don't want all of them, right? Filter them. I only want the ones that match this criteria, right? So as you consider all the possible combinations, right, compare certain fields in those combinations, against each other, right? And they, compare and see if it makes the predicate true in the where clause. If it is true, I want that record, right? So in the previous where we had all the records, right, from various tables, and we have several tables, and you have records and records, right, that were cross multiplied, and we have all the various combinations. So if we have 10 here and we have 10 here, we end up with how many here? 100, right? There's 100 possible combinations. Yes. So that's the top half, the select and the from. Right? It considers all possible combinations. Yes. But in the where clause, it says I don't want all 10 because probably most of them make no sense. Right? Like the persons and the orders. Some of them didn't make sense. Right? So the where clause says I only really want that one, that one, that one, and that one. Right? Because those are the only 4 out of the 100 possible that make my predicate true. Right? So that where clause filters those possible combinations and whittles them down to only those that make the predicate true. Okay? So in the where clause, you can have all sorts of operators and say, Boolean operators, right? That allow you to create these expressions, these Boolean expressions saying, is this equal to that? And what about that? Is that equal to that? Or is that bigger than that? Or allows you to compare and create these predicates, right? So in the where clause, you can use operators such as, is it equal? Is it not equal? Is it greater or less than, and whatnot, right? Or also you can check for ranges. Is the value between these two other values, right? Or if I have a set of value, is that particular value in that set, right? So you can compare against several values at the same time. Or is it like, right? Is it pattern matching against a string, right? And then you can combine all these predicates with ands and ors into a larger Boolean expression. So for instance, here's one that a very simple one. Select star from persons, right? So what does that do? That returns what? It returns all the records, right? So it returns all 3 records. But I want to filter only the ones who have the city equal to Lowell. Right? That only returns 2 records, right? Or I can combine it, right, with where I would say where the first name is Bob and the last name is Dole. Obviously, it returns only that one record, Bob and Dole. Yes, right. And or I might say where the first name is Bob or the first name is Dan, right? That then returns 2 records. Those 2 records make the predicate true, right? Well, notice that this is all inside of a single table, right? Over here, and here's the one that we can combine, right? We can say, well, the last name is Doe, and the first name is Bob, or first name is Dan, right? In that case, let's see. First name Bob or first name Dan, that means that it's those two records, 1 and 2, make this piece of the predicate true, right? But then this shortcuts the whole thing, saying that I only really want the ones that has the last name Doe, right? So it returns only that one record. Right, so we had said earlier that in the join, that the joins, wait a minute, multiple joins record. Right, so in the where clause is evaluated after the from, right? So the from says these are all the tables, right? These are all the tables that are being considered, right? And it says these are all the records that are being considered, and I am cross multiplying all of them. So I am considering, if we have 40,000 students and we have 20 departments, I am considering 800,000 possible results, right? Here in the from, right? And I am looking at all the fields, right? So I'm looking at all the fields in the student table, and I'm looking at all the fields in the department table, right? I haven't gotten to the select part yet, right? Where this one tells me, hey, I don't want all those fields. I just want the student name, right? So this from looks at all the possibles, right? If it's one table, it's obviously I'm looking at all the records in that one table, right? But if I have two tables, then I'm looking at the cross multiplication of those two tables, right? So here I'm considering all the records, all the fields. So when I get here, I have all the fields at my disposal, right? I can look at all the fields in that table. If I have more than one table, I can look at all the fields in all the tables, right? In the where clause to do all my comparisons, right? So this where clause gets evaluated after the from, after I identify all the tables, all the records, right? So this whittles down and says, no, I don't want all the records. I only want the records that have this predicate equal to true. Now that I have the records, meaning I filtered vertically, now I go back to the select and I say, I only want a subset of the fields. I don't want all the fields. You had all the fields in the where clause. Notice that I have graduation year. I can have the department. I have everything here in the where clause, right? But then I filter and says I only want that particular field, right? As I said earlier, we can use the where clause, the implicit, to make it more readable for the joining, right? There's a little bit more readable. The bottom one is a little more readable than the join at the top. We call that the implicit. But not only can I use it to filter on things that are primary key and foreign key, right, to join, but I could use filter on other fields that are not, they don't have any constraints, right? Like on the student name and the year, right? So I can filter on, my predicates can contain foreign key, primary key relationships, but I can also combine them with other things that are not constrained, right? Like the year and the year was offered and whatnot, right? Between allows you to pattern match, retrieve records that you can compare a value in your field and to see that it matches, that it's within a particular range, right? So for instance, and they could be either numeric or they can be alpha, right? They can be in dictionary order, right? In dictionary order or lexicographical order, right? So for instance, I want those those records that whose last name is between Boone and Garcia, right? And wait, it's supposed to bring Bob Dole. That's wrong. All right, I'll have to fix that. Not between Boone and Garcia. Not between. So, well, this returns everybody else, right? It returns everybody else. So that would return, right, Boone and Garcia. That's okay. That's wrong again. All right, I have to fix these two. Keywords allow the in keyword allows you to compare one value, right? One field, values in a field, compared against several other values, right? It says, here's a column A, and it says, and I want to compare that particular value and iterate over all those values, right? If it's equal to any one of those values, it returns true, right? And then I want that record, right? I want that record. Notice that it has to iterate, right? It has to go through each one of them, and it'll shortcut, right? The first one that it finds, the whole thing returns true, meaning it's not going to iterate over the entire thing, right? The first one that it finds that makes the whole element true, it just returns. So for instance, last name, okay, this is, all right, I think this one's correct, right? It says, I want the ones whose last name is in Boone and Garcia. So it's going to iterate over these two. So notice that for each record, so this is expensive, huh? This is expensive. It has to, for each record, it has to iterate over here. Is it equal to Boone? Yes. Oh, I want that one, right? Then it goes to the next one, Dole. Dole, is it equal to Boone? No. Is it equal to Garcia? No. Okay, so I don't want that one, right? So it has to iterate. So for each record, now imagine iterating over 40,000 records of students, right? And looking to see if it's in something, right? So now it has to iterate over the elements in this array of literals, right? So yeah, so it's expensive. Like is also somewhat expensive, right? Because it has to compare the string against a pattern match, right? So here it is. Student name, like, so anything that starts with a J, right? Then I want that record. Plus, I want to do some date operations. I want to take the current dates, right? And that becomes a year. And then, so notice that I'm doing this. This operation is expensive, and I'm doing it every time I iterate, right? For each record. So if I'm doing this 40,000 students, I am extracting the year 40,000 times. And I'm always going to get the same year, right? So ideally, we would want to put this maybe in a variable, right? Calculate it once, right? And then use that value here just once, right? We'll look at using variables a little later, right? That you can replace this and things like that that would allow you to improve performance in these, right? Here, we're extracting those students that are enrolled in a particular in sections, right? And we're filtering. Notice that here we're joining, right? These two equals, for the first two equals are joining the three tables, right? Joining the student, the enrollment, and the selection table, and the section table, right? Whereas this one is filtering by professor, meaning first join everything, right? So I know all the students enroll in what section, right? But again, it might be lots and lots of students, right? Yes.
So seeing this, isn't where better than join, because we can actually compare more than 3 tables.
Right. No, but this one would have an equivalent join, right? Well, you would use join to do these 3, and then use the where for this one over here, right? Right. So yeah. So there's always an equivalent, right? Whenever you are, this is a join, which can be used using the explicit syntax, right? You can students join with enrollment on student SID equal to that parentheses, right? Join with section on, right? E section blah 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 blah, right? But this is much easier to read. It's definitely much easier to read. Constraints. Right. So we already looked at some constraints, right? We looked at primary and foreign key, definitely, right, to create the relationship between the two. Now, those remember, the reason why we even use primary key and foreign key, right, is that, again, we're asking the database, right, for its help to ensure referential integrity. I mean, all these queries would have still worked, right? All these queries would have still worked, even if we would have not declared these student IDs as primary keys and these student IDs as foreign keys. This would still work. Our database still works just fine, right? If we don't use any foreign key and primary key, right? The reason why we even do it is to say, hey, database, these are special fields, right? we are giving it meaning, saying, hey, there's a parent-child relationship between these two fields, right? Right? And don't allow me to do things that make no sense, right? So we're asking the database to please validate, right, that if I'm inserting a child, that there is a matching parent, right? If we don't declare these to be foreign keys and primary key, it would just allow me to insert things, right? Like we had an order, right, that had no person, right? The only way to allow that is that those fields were not declared as primary keys and foreign keys. And the database is just going to let me do that, right? Whether I want the help from the database or not, right? That's my prerogative, right? Usually we do want the database to help us, make sure we're not inserting bad data or bad relationships, right? Again, all this would work without primary keys and foreign keys. We use those constraints to have the database stop us from doing stupid things. Other things, not null. I don't know if you've seen that already, but I'm guessing. We just like you have a form in a web form. Typically, some fields are required, right? You're logging in. Well, you have to give me the username and password. I'm not going to let you through if you give me one but not the other, right? So same thing here. We can enlist again the help from a database to say, hey, don't allow inserting a record if you don't have this field, right? If you don't have a value for that field, it just makes it, I don't want it. Don't give it to me. Don't insert it in the database. So I could label certain fields that they are I will reject records whose a particular field is null, right? So the way we do that is next to a field, we would say not null. This cannot be null, right? Unique, we could say that a particular field has to be unique. When we declare something to be a primary key, we're already saying that it's unique, right? But we might have certain fields that we are not primary keys, yes? Remember, primary keys is because we want relationships, right? We want something is relating to this thing, right? So it has to be unique, and there's a relationship. But there are some fields that have to be unique, but they're not necessarily a primary key. Maybe a phone number, right? It makes no sense that I have a phone number and you have exactly the same phone number. That makes no sense, right? But it's not a primary key. Nobody's referencing this, right? I just want to make sure that I'm entering good data, and I want to enforce the fact that we have unique phone numbers or emails, right? It makes no sense that we have the same email, right? So I would like to stop you from entering bad data. So unique allows us to put it next to a field that has to be unique. Check allows us to do some if then else values. Make sure that if you're going to insert an age and I declare as an integer, well, make sure it's positive. Don't give me an age that is negative, right? So check allows us to make sure of those things, right? Check that is positive, right? If it fails that predicate, then don't let me insert that data. Things like that, right? And default allows me to give values, default values to certain fields. So for instance, here, PID int not null, right? We're explicitly saying that for the primary key, well, it cannot be null, right? It has to have a value for that. Also, last name, you have to give me a last name, right? Over here, we're saying that that primary key has to be unique. Now, when we declare something as a primary key, it is implied, right, that it is unique and it's not null, right? It's implied, right? So there's different syntax, right? So if you're using MySQL, the syntax is that it's in a separate line, right? If you're using SQL Server, you can use either, or you can do it right next to the field, right, that you want it to be unique. So these are constraints. These are all constraints, right? You're saying that something is unique, that something is not null. You're constraining the data. You're constraining, meaning I will not accept data that I will not accept a record that violates these constraints, right? Or I won't allow you to change the data, right, if it violates these constraints. Now, constraints, these are all anonymous constraints. They don't have a name, right? We don't have a name. but you can name them, right? You can name the constraint. So here's a constraint, right? You're saying that the combination of PID and last name is unique, and I'm giving it a name. I'm giving it a name, right? It's not required that you name your constraints, but sometimes you want to be able to modify constraints, right? Later, right? Using, once the table has been created, I would like to maybe alter that constraint, yes? And to be able to alter it, I need a name, right? Because I need to be able to refer to a constraint and say, hey, that constraint over there, I want to change it. If I don't have a name, I would have to change the schema, right? So altering needs names. Primary key, we looked at already. We're saying that field over there, which already has a constraint not null. In addition, I'm creating another constraint on it. I'm saying that it's a primary key. Right here's in SQL Server, you can put it next to the field, or you can name that constraint. Right, you give it a name, or you can say that it's a foreign key. Right, you're saying that this table orders, right, this PID, right? This PID is referencing, right? It's that field here in this record is referencing some other table with that field over there, right? And they could be named the same, right? But they don't have to be. This PID could be called something else. Right? Some people like to put in front of it order to person ID, right? Saying that, oh, this is a reference that goes from the order back to the person, right? Right, so that's one of the syntax in MySQL. Right, here's the way you might do it in SQL Server. And naming your foreign key so that you can change it later on, perhaps with an alter command. If it's referencing, if you have a field that has two primary keys, so primary key 1 and primary key 2, right, where this is referred to as a compound key, right? And you have a table that is referencing that records in that other table, right? Those foreign key also have to be well, they don't have to. They can refer to the combination of primary keys in that other table. So these two fields, reference column 1 and 2, are referencing two records that live somewhere else in some other table, right? And presumably that combination is unique and is declared as a primary key combination on that other table. Default, right? Meaning that if you don't give me a value for city, right? If otherwise this would be null, right? Because you left it out, right? You didn't type in the city name, I will default it to Lowell, right? So if you insert a record that does not have a value for city, right, it will default to Lowell. You can use that technique to timestamp a record, right? For instance, you might timestamp the date in which the order was created. So whenever it's inserted, right, the date that was created, it will, by default, computer will use the getDate method, right, to get the date at which it was created, and that's the value that it will use, unless you give it a value. If you give it a value, it will use whatever you give it. If you don't give it a value, it will default to today's date. Okay. Auto increment. As you're inserting, some fields are required, right? Certainly, the primary key is required, right? Because usually, primary keys cannot be null, right? They have to be unique, and they can't be null. So you have to give me a value. And that becomes a little annoying that some of these values are just 1, 2, 3. It's just the next one, right? So most databases have a mechanism by which we can let the database choose what that primary key is. As long as it's unique, I don't really care the value what it is, right? As long as it's unique, Oftentimes these are for primary keys that are artificial keys, right? Keys that are there just to make sure that they're unique, right? And that there's being referenced by someone else, right? If it's a key that I know it's unique that I am generating, maybe I'm using the email as a primary key, then I am providing the email, obviously, right? I'm giving it to you. So obviously not auto-generated. But if it's an artificial ID, it's okay, right, to make it auto-incremented. So this is how you would do it in MySQL. You would say that this is auto-incremented. You can by default it starts at 1 and increments of 1, so it's 1, 2, 3, and so on and so forth, right? But you can change it. You can say, well, start at a different starting point and then increment by 10, say, right? So you can start at 100 and then increment by 10. So it's 100, 110, 120, so on and so forth, right? This is very useful, for instance, when you're data migrating, right? And you're migrating 20,000 records from a legacy database, and you import the first 20,000, and then every new record, it's going to have to start at 20,001, right? So you can say, well, okay, so import the first 20,000, and then auto increment starting at 20,001 by 1, right? So auto increment, and here's how you would do it, perhaps in SQL Server, with the option of starting at a particular point, right, and then incrementing thereafter. They're using the identity keyword. So when you actually insert a record on a field that is auto incremented, what do you provide, right? Well, if it's for instance in some databases, you can insert and just omit the field altogether, right? And it'll say, oh, if you didn't give me a value, I'll just increment it. Okay. In some other databases, you have to explicitly provide null. Okay, you have to explicitly provide null. It says, I am deliberately not giving you a value for the primary key. I want you to provide the value for the primary key. If you are providing the field names, you say inserting into these field names, and these are the values, you can get away with not providing the field name for the primary key. If instead you're not providing the names of the fields, right, that there's no mapping, it'll assume that the first one is the first field, declaring the create statement, and this is the second field, declaring the first and the create statement, and that's the third field, and so on and so forth, right? If you're using this syntax for the insert, you have to provide null for the first one because it's going to assume that's a primary key, right? So you have to provide the value for that, for the null value. Oracle does not support auto increment. They instead use what is called sequences, right? They create a whole different table where they pre-compute all the values already there, right? So they'll say, start at 1, go to infinity, right? Or it'll be some really, really big number, which are pre-computed from where we're going to grab those keys, right? Those values for those primary keys. So we create a sequence starting at a particular value, going off to some forgotten place, really, really large value. And then when we're inserting, right, we use the keyword, the object sequence, the name that we gave the sequence, and we say, oh, okay, well, use the next value available. And it keeps track on which keys, which values have been used so far, right? So it keeps track of which one so that it knows that the next value is the next one in the sequence, right? I'm not sure why they're using sequences. Auto increment looks like a very much better solution. Okay, there it is. All right. Went through queries. Subqueries, self-joins, pagination. What do we have here? Let's see. Oh, yes. Okay. Yeah. Right. So Right. So we mentioned earlier the fact that we could have that when we do a query, right? When we do a query, basically it generates a table for us, right? It's a table. It's a subset, right? Out of all the various tables. Maybe we have 100 tables, right? And each table has thousands of records, right? The select statement generates for us, right? A subset of all that, right? Maybe some data from one table, some data from some other table, right? Some records from one, some records from another, some fields from one table, some fields from another, and it generates what does it generate for us? Something that looks very much like a table, right? Has fields, has records, right? And values for each one of those records. Well, it can actually that select statement that generates this kind of pseudo table, right? This temporary table can actually be treated as if it were, right, a table on its own, right? If it generates several fields, right? If it generates several fields and then several records for that field, it's a table. But if it generates a single field, right, a single column with various values for that one column, it can be treated as an array, right? It can be treated like an array as opposed to you have a single dimensional array or a double dimensional array, right? So you have a table or a single array. So over here, for instance, if you have here's a select statement, right? Which is gonna retrieve what? A single field. You see that? It's retrieving a single field. That means its result is going to be like an array, like a vector, right? That has different values. Well, that vector of values can actually be used as part, right, in the in clause, right? That says, hey, you've computed all these various values. I want to have an outer select statement. This outer select statement, right, is reusing the values of this inner nested query, right, as part of this in the where clause, right, as part of the parameters for the in, right. So here we have an example of using the select statements in the where clause, right. So you can use the nested select statements. Yes.
So I have one question regarding that.
Yeah.
So for it to delete all the rows present in the table, so what exactly will be the value when this record after we delete all the rows?
It'll just be the next one.
For example, we delete the middle one.
Yeah, it'll start from wherever it had left over. Yeah, it'll remember where it was left over. Yep. Right. So in a second, I'll show you an example where the select statement can be used not only in the where clause, it could be used right here in the from. Okay, it could be used in different ways, right? Over here, now if you're using you have a question somewhere? If it's returning a single value or a multi-valued, right, like an array, it could be used in an in, right? Or if you know that it's returning a single value, it's returning a single value, right? Maybe you're retrieving a person and you have the primary key of that person and retrieving that one person and returning the last name of that person, right? If you know it's returning a single value, then it could be used as in, table field equal, right, to that one scalar value. Right, one single value. Right? So again, it could be a single value, it could be an array, or it could be a double, right, a two-dimensional array, the results. And depending what it returns, right, you can use it in different contexts. Okay? All right? So here's an example where we have, select ID, first name, from student details where the first name is either Alice, Bob, or Charlie. Okay, and I know that Alice and Bob and Charlie are all in the science program, right? And I just remember that those are the 3 students that are in science, right? But say somebody else joins or somebody leaves, right? My query, the top query is hard-coded, right? And it would be a maintenance nightmare having to, says, oh, there's somebody else in the science department, blah, 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 add it, remove it. Instead, I can generalize it and say, hey, you know what? just retrieve everybody, all the first names from the student details where the subject is equal to science. That returns an array of all the students, right? Presumably, right now it's only Alice, Bob, and Charlie, presumably, but it could grow, it could shrink. This is much more generic. It could be reused as new users are added or removed from the student details table. Yes.
Going along the lines of what you said, first from is evaluated, then where, right?
Yes. First from, then
So
where.
when we have a subquery, is it correct to understand that the subquery is evaluated first and then again goes on from where and then?
No, first from is declared.
Always.
Yeah, always. Yeah, from, and then once you have those records will be compared against whatever the inner statement is. Yep. Yep. Okay, so here's another example where you have a list of several countries, their region, their geographic area, their what the. Sorry about that. Okay, I hope that. What was it saying? What was it saying? Right, so these are countries and their geographic region, their geographic area, and their population. Right, at the time the slide was generated, and their GDP. So for instance, internally we can have an inner query where it returns a population where the name is Russia. Notice that this returns exactly one value. Right, this returns a scalar value, and we're comparing. Where I want to know the GDP where the population is greater than, whatever Russia's GDP is, right? And that returns a name for that, right? GDP where population is greater than Russia. So it was returned all the records, all the names of the countries whose GDP is greater than where the population is greater than the Russia's population. I hear hello. You have a question? Yeah, it's very distracting, the background noise. Let's just have one conversation here, unless you have a question. So here's an example. So we saw two examples, right? One was an array result, right? The other one was a scalar, just one value. And here's where it's a two-dimensional results set, right? We have several fields and several records, right? So in that case, it could be used in the from. Right, see that? It can be used in the from, where the inner returns, by the inner here, right, the select over here, from here to here, returns a table, like if it's a table, right? And we call those inline views, something that, it's a table that comes into existence, right? It's used and then thrown away, right? And so what are we doing here? So in the inner, notice that it's extracting from the orders. It's retrieving two fields. One is a supplier ID. The other one is something, right? Some other field, total amount, using some summation, some aggregates that we haven't looked at just yet. But it's two fields, right? Supplier ID and total amount. So it has two fields and several records, presumably, right? So it's a table, right, with two columns and many values, many records in there. So it's basically a table, like it's a fleeting table that comes into existence. We briefly give it a name, subquery 1. We briefly name this table subquery 1, so that we can then use it outside, right? We can use it outside. Again, the from is evaluated first, right? Once we have identified all the records, we're going to filter. We're going to filter outside and say, okay, we only want the ones where the supplier of the inner record, right, of this field that was generated is equal to the outer suppliers table, right? So we are pattern matching fields that are being generated on the fly inside of this table, right? And we're matching those against fields that are from another table that exists, right? From this suppliers table. And then I'm going to keep only those records from from this predicate. Okay. And here we have a select statement being used in the select clause, right? So we can use select statements in a whole bunch of places, right? We can you could use it in the where clause, right? Where it can be either a scalar or it can be an array, right? In the from, it would be treated as a table, even if it has one column, it would be treated as a table of one column. Or over here, where it has to evaluate to a single value. It has to evaluate to a single value, and that one value will be used as a result for that field, right? In this case, the field is called subquery 2, right? So that means that as we are iterating, right, as we're considering all the various records from all tables, right? So I guess that's presumably several tables, right? Several tables are being considered, are going to be joined. So as I am iterating over this over here, right? Notice there's no where clause, right? So I am not filtering, meaning I am going to look at all the records. I'm going to return all the records. As I am iterating, I'm going to return only those fields. Let's see, I'm returning only the owner. So here's owner. I'm only returning the owner. I'm only returning the table name, right? Plus, I am generating another field, subquery 2, right? Subquery 2. So I'm generating 3 fields. I'm returning 3 fields, right? The first 2 fields are obvious, right? Those are fields from the original table, right? Whereas the third field is what? Let's see. It says that we are looking at a table called all table columns, right? So we're iterating over that, and we're out of those. So there's some other table, right? Some other table. We're iterating over that, and we only want the ones that match the owner here, right? Matches the owner field there, right? So as I am iterating, I am comparing each one of these values against that particular record that I'm looking at, right? I'm only looking at that. Once I filter that, what am I doing? And also table names match, right? So I'm looking at the table name here and the table name here. If they match, I want that record, right? I want that. And I am counting how many, right? The outer says count, right? I am counting. So if this one match and that one match and that one match, there's 3 matched. So I count as 3, and that 3, I am naming that 3 as total columns, right? So so this 3 over here, I'm naming it total columns, and that result is it's only one result. When you count, it's just only one value, right? And that's being renamed as subquery 3. So that 3 comes out over here. And then when I go to the next one, I'm going to do the whole thing again. I have a new owner, a new table, and I reiterate over this, right? Iterate over this. I compare, I look, I count, it comes out to 5, right? And this becomes 5. Yes? That makes sense? Okay. Union allows us to combine results from various queries, right? So for instance, I might query a table of students and tables of staff, right? And I'm we're going to have sporting events. We're going to go golfing, and it's going to be students against staff members, right? And so we want a table of all the members who are going to participate in this golfing tournament, right? And I want to query, but the students are stored in one table, and the staff members are stored maybe in another table. Okay, So I want to go and combine the two into a one result, right? So I can go off and query the student table that has student name, blah blah blah, right? Retrieve their age, blah blah, and then query the staff table, and the staff table has it doesn't have a field called student name, right? It has maybe faculty name perhaps, right? But I want to combine them into a single result. Right? How do I combine them? Right? If I would want their names, their first name and last name, to be on a single column in the resulting table. Yes, right. But the fields are called student first name in the student table, and in the faculty they're called faculty first name. And I want both to end up in just first name, right? So what I need to do is so for instance, I might select the columns that I need from table 1, the columns that I need from table 2. I can only put them in unions if the columns match, right? If the columns match. So we already know how to rename fields, right? We can use the as keyword, right? As we're selecting from the student table, the student first name, we can say as first name. Right, as we're selecting from the student table. And as we're selecting from the faculty table, the faculty first name, you can say as first name too, right? So when you do the union, it basically concatenates the results of the first select. It concatenates it with the results of the second select, right? And it gives you one big result, right? If you don't name them the same, then they end up being separate columns. Right, separate columns. Right. So, for instance, in this case, we have employees in Canada, employees in the USA, right? And the fields happen to have the same names, but they don't have to, right? Because we always can rename them as we select. And notice that Stephen Doe works in both offices, right? Sometimes he works in Canada, sometimes he works in the U.S. And when we do the union of these two, we notice that Stephen Doe, by default, union does not keep the duplicates, right? By default, it says, oh, Stephen Doe was already there. I'm just going to throw him out. So this one returns the one e-name, unless you say, I want the duplicates. Give them to me anyway. I don't care. So you can say union all and returns also the duplicate keys. You can also order by. Order by allows you to sort, right, the result set. Now, you should never assume that the data itself, when it gets stored, it's sorted in any particular way, right? Data is inserted presumably in the order in which they were initially entered, right? Which cannot be guaranteed to be in any particular order, right? In any case, you should never assume any order of the data. You should assume that it's just a set, right? And there are no preferences. But for human consumption, for our benefit, we might want to see things in a particular order, right? Order it by last name, right? Order it by city, order it by zip code, right? So this allows us to generate a result set that is in a particular order, either in ascending or descending, right? And you can have that in just one column. You can say, column 1 ascending, column 2 ascending, column 3 descending, right? So it allows you to combine several columns. So for instance, over here, we can say, select all the persons, but order them by last name. So we have here that initially they were not ordered, right? But when it generates it, we have Boone, Dole, Garcia, and Nilsson. Or descending, right? So it goes backwards, Nilsson, Garcia, Dole, and Boone. Self-joins, if you remember, what allows us to have relationships with records that are on the same table, right? If you remember, we gave you an example earlier where, that was it. where you might have an employee table, right? Where you might have one-to-many relationship with other tables, right? Here, so here might be the department having a one-to-many, right? But you might also have records that are related to one another in the same table, right? So you might have, these three reporting to the same, team lead here, right? And so the way we represent this, the way you represent that is you have a foreign key back to this primary key over here, right? The way you represent this is that you have another foreign key. Right? So you have foreign keys. All these foreign keys tell me that all these guys work in that department, but this other foreign key tell me that these three, right, report to that one person. So you have two foreign keys, one to another table, and another foreign key to the same table, right? Okay. So those foreign keys allow you to, again, create relationships between records on the same table, and it becomes a little challenging, right? To just like you can join departments and employees, it's a little challenging that you need to also be able to join, employees with employees, right? Because just like you want to find out, who works in what department, you might want to find out who works for who, right? To create an org chart or something. So here we have a category. So categories typically these self-referencing data models allow you to create hierarchical representations, right? Things that have parent, and you have children, and those children have children, those children have children, right? Where you have kind of like a recursive definition, things where you can have some kind of root, right? And then you can have several branches, and then you have those leaves that have no children, right? So these self-referencing, right? Usually we capture this in the UML as such, right? Where you have the self-referencing over here, right? Allow you to create these hierarchies. So here's a category. If you can imagine, Amazon, right? Where you can have several top level categories, and then each category having several subcategories, right? And those subcategories having, again, lots of other subcategories. So this would allow you to notice that to represent this kind of data, we have the primary key, the parent ID, right? That's a primary key, and then you have a foreign key. No, I'm sorry. The primary key is the ID up there, right? That's the primary key. And then you have a parent ID that says, each child knows who their parent is, right? So you can navigate backwards and forwards between parents and children. And the way it references, notice that here's a self-reference, right? We're saying that me in the category table, I am referencing the same category table, right? And I'm self-referencing myself into my primary key, right? And that allows me to create these hierarchies. So for instance, you might have a top level category, top, and you might have that it has no parent. It has no parent ID. That's how I know it's a parent. And then you might have, and these are all auto-incremented, I believe, right? Yeah, it's auto-incremented, right? So as I insert in the record, the ID is auto-incremented. So notice I'm introducing two top-level categories, electronics and movies. Those are two top-level, right? Who their parent is the top level, right? And then we're saying PCs, I'm saying that the parent is 2, which is the electronic, right? And then I'm introducing DVDs, I'm saying that the, I guess the PCs, DVDs, PCs, really? Okay, whatever. And Blu-rays also is PCs again. Maybe that should be a 3. How's that? Yeah, that should be a 3. Yeah, this should be 3, and this should be 3, right? There we go. So now notice that I can if I want to choose, if I want to find out whose parents who's a child of what, I can say select all the children, right? And I'm going to join what? I'm going to join the foreign keys of categories with the primary keys of categories, right? So I need to, as if they were separate tables, but they're not, right? So here are the two tables, categories child, and then categories parent. They both happen to be from the categories table, right? Where the parent ID matches the parent ID, right? So whose child parent ID matches the parent ID, right? And I want to know where the name of the parent's name is movies, right? So this would return the children DVDs and Blu-rays, right? It would tell me that hierarchy. Right? Enums, enumerations allow us to enforce that certain fields can only have certain values, right? For instance, integers are enumerated data types, right? They're just a very big enumerated data type, right? They go from minus, 4 billion all the way up to plus 4 billion, right? So it's a big enumerated data type. You can only have those values, and they can't be floats, right? They have to be 0, 1, 2, 3, blah, 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 up to 4 billion, or all the way down to minus 4 billion, right? Whatever size of bytes you're using to represent integers, right? So enumerated data types allow you to have the same thing for strings, right? I want this data type, the value of this string only to be taken from this approved set of values, right? And most databases support what is called an enumerated data type, right? That says it's not a varchar. If I say varchar, I can put anything in there, right? Right? I want to restrict the possibilities here. Maybe their roles, right? Somebody's role. So you can be an admin, right? You can be a team lead. You can be a project manager, right? So when you choose the role, I wouldn't want you to be able to just type anything, right? I like you to select from a vetted list of values, right? So enumerated data types allow you to do that. The thing is that this syntax is not supported by all databases, right? Not all databases have the enumerated data type, right? MySQL does have it, but I would suggest that you do not use MySQL's enumerated data type, even if you are going to use MySQL, right? Instead, use this other implementation, right? This is it's a portable implementation of enumerated data types. Right? What you do is that first you create a separate table, right? So those values that are the approved values are going to live on a dedicated table, right? So for instance, genres, right? So we have comedy, drama, and horror. Those are the only 3 genres that my database supports, right? So we declare a table called genre. And we make it a primary key. That means that we cannot have the comedy more than once, right? So these are all unique values. I am enforcing this to be a unique value. Also, this is going to be a primary key. That means that somebody's going to reference this, right? Somebody's going to reference this. And then I insert the only approved values into that table, right? So it's going to be a very small table, right, with very few records in there, right? So it's going to be comedy, drama, and horror. So that's my enumerated data type now, right? Now, whenever I want to say, just like over here, I say that name can only be small, medium, or large, right? Meaning, I want now a variable and say this variable can only have comedy, horror, or drama, right? So how do I do that? Okay, so I have my enumerated data type. There it is, right? Genre. So later, the way I would do is that I create a table and say where I'm going to insert a whole bunch of movies, right? And one of the fields of the movie, besides title and rating and whatever, right, is its genre, right? So I declare my genre. I declare as a varchar, right? That would seem like I could type anything in there, but no. I'm going to say that this genre, okay, it's varchar, meaning it's going to store the character, the strings, horror, movie, whatever, right? But it's going to stop me from entering anything other than those three things. How? Because I am going to make it a foreign key, right? And I'm going to rely on the database's a referential integrity mechanism, right? That is going to make sure that it will only allow me to enter data there if it exists as a primary key in the genres table, right? And so what you end up having is that, here's a movies table, right? So here's a movie table, and you have all these records, right? And here you have the genre where you have horror, comedy, and drama, right? And this one says, oh, I'm horror, and oh, I am comedy, and this one, oh, I am horror too, right? And this one is a drama, and this record over here is another horror. I like horror movies, okay? Right? So that means that as I enter it, right, I can never type anything other than these three values. You see that? Right? So that's how I am enforcing, right? So I have the same functionality of enumerator data type, but implemented in a generic, portable way, right? So I can take these two tables, right, and port them to any other database, right? And I'm not relying on a vendor-specific implementation of enumerator data types. Okay, so yeah, so you have these two tables. Right? Okay, that's that. Yeah, we've got 4 more minutes. All right, let's leave it here. So this weekend, I'm gonna make available an assignment in Blackboard where you're going to provide your description for your project. Okay, so provide also the team members, right? The team members, and then a couple paragraphs, right? What your idea is for the project. Some of you might have more than one idea. If you have more than one idea, also provide it there as well. Ideally, the easiest thing for me is that it would be, maybe you already have it in Word, but if you have it in Google Docs, you can just, submit the link to the Google Docs. That would be the easiest thing, right? Instead of storing PDFs and Word documents in Blackboard, you can just click there and go see the documentation. Okay. Maybe you want to give me permission to edit, right? Where maybe I can provide you with a response, or maybe I can provide some comments on those documents. Okay. All right. What else? Also, we're thinking of pushing the assignment due dates by 1 week. Just because, again, with the winter storms, perhaps you didn't have enough time, to maybe ask questions about the assignments. So we'll try to just move them. They're every 2 weeks, but let's synchronize them with the storms. So we'll make it due next. What was it due tomorrow?
Yeah.
All right, so we'll make it due next Thursday. Okay. All right. Thank you.